Let's continue with some examples of trigonometric substitution. So now we're going to take a look to certain integrals where we can use the other possible trigonometric substitution that we declared before. So we mentioned that we can use these expressions, and we're going to use this substitution dependent of these expressions. Okay, so we're going to have a sine of theta. If we use this a squared minus x squared, we're going to use a tangent of theta. We have a squared plus x squared. And we're going to use x equals a secant of theta if we use x squared minus a squared. So now we're going to see initially these examples of how to approach those. So first, let's go with the integral from 16 minus x squared. This clearly is something of the shape a squared minus x squared, where a is going to be equals 4. So a squared becomes 16. So this means that the trigonometric substitution that we're going to be using is x equals 4 sine of theta. And so because of that, then dx d theta is going to be 4 cosine of theta. And then the x is, of course, 4 cosine of theta d theta. We transform that into the integral of 16 minus 16 sine square of theta times 4 cosine of theta d theta. We're replacing the dx, and we plug in here to get the factor. Now, in here we do the same thing that we did before. We factor the 16 since it's a common term in there, and we get 1 minus sine square. Now you can see at this point that 1 minus sine square is of course going to be cosine square. And so this transforms into 16 cosine square of theta times 4 cosine of theta. And then this is going to be 4 cosine of theta times 4 cosine of theta. So that will mean that this is equals to 16, the integral of cosine square of theta d theta. And so now this is one of those integrals that we can use identities to support ourselves. And we're going to be using double angle identities to transform cosine square of theta. And then cosine square of theta is transformed into 1 plus cosine of 2 theta over 2 using the double angle identity. And so now we can pull out this 2 over here. We get an 8. And then we're just left with 1 plus cosine of 2 theta d theta. We can integrate that easily, of course. And that's just going to be 8 times theta plus, and the integral of cosine is sine. And so this is going to be 1/2 sine of 2 theta. And we're pretty much done. At this point, what we need to do is put this back in terms of the original variable x. Notice that we have sine of 2 theta, and that's equals to, if I just write this, sine of 2 theta is equals to 2 sine of theta cosine of theta. And so I need to find out who theta is in terms of x. I need to find out who sine of theta is, which I can find really easy. Remember, I get this substitution, and then from here I can get first x over 4 is sine of theta, so we got that factor. We have also that theta is arcsine of x over 4, so we got this piece. And now the last part is that we need to find out who cosine of theta is. But cosine of theta is easy because we know that cosine of theta is a square root of 1 minus sine square of theta, right? And so we can use the fact that we know what sine of theta is, and this is going to be 1 minus And sine of theta is x over 4. So this is x over 4 square. And so this can be simplified as 16 minus x squared over 4. 16 over x squared over 16, of course. But when we take the square root, then it will be over 4. And so this will be the value of cosine of theta. And then we can replace what this is here. 8 and arcsine of x over 4 plus, and this is 8, and then sine of theta, which is x over 4, and cosine of theta, which is 16 minus x squared over 4 as well. There can be some simplification in here, of course. This is a arcsine of x over 4, and this 8 goes away with this 4. This is going to give me a 2, so this will be just simply x 16 minus x squared divided by 2. And then we can add the plus c, of course, at the end, and that will be the end of this particular integral. Now let's move on to another example. Now let's transition to the integral of 1 over x squared square root of x squared plus 9. So notice that this is the x squared plus a squared type of substitution. And according to what we mentioned before, this got a substitution of the type a equals tangent of theta. Over here, a squared seems to be 9. So that means that a will be 3. And so x is going to be 3 tangent of theta. And so dx is going to be 3 secant square the theta. Okay? Doing that transformation, we get that this is 1 over, and this is 9 tangent square of theta. And this square root of 9 tangent square of theta plus 9. And then we'll multiply by the dx, which is 3 secant square the theta. Notice that we're trying to achieve a way to cancel out terms. So we're going to factor here as usual. And we're going to get 9 tangent square. And over here, of course, we get 9 tangent square plus 1. And of course, tangent square plus 1 is just another way of writing secant square. So for the next step, I can cancel one of these 3, one of these 3, and I'm going to get secant square. And now over here, I'm going to get 3 tangent square. And the square root of 9 is going to be 3, so I get out another 3. And I'm going to get square root of secant square of theta from the tangent square plus 1. And then that's going to be equals to, now here I'm going to get a secant. So I'm going to get secant square over 9 tangent square, and I'm gonna get a secant here. I get to cancel one of the secants, and so I'm going to have secant of theta over 9 tangent square of theta. One way that I have to approach this is just simply separate what secant and what tangent square are in terms of sine and cosines. So for example, secant is something that I can write as 1 over cosine. And now this tangent square is sine square over cosine square, but notice that because it's below, that I can flip it as cosine square over sine square. And so now that I have it in here, I can cancel out one of the cosines. And what I have left is cosine of theta over sine square of theta. And this kind of prompts a substitution here, where I can say, well, u is equals sine of theta, and then the u is going to be cosine of theta, u theta. So I have the du clearly in there, and I can just see this as 1 over 9, 1 over u square du. And then again, this is a power, so this is 1 over 9 u to the minus 2 du. And integrating this will be 1 over 9 u to the minus 1 over minus 1 plus c. Okay. Now to finish up, then this is 1 over 9, and then this this minus can be put in from, so minus 1 over 9, and this u to the minus 1 can be written as 1 over u, and I can just go with 1 over sine of theta directly, since I can just write what the u is. Now here is a little bit simpler than before, because we had that x over 3 was tangent of theta. I can think of this as the ratio between the sine and the cosine, right? And so this is like this side over this side, like y, and this opposite side over the adjacent side, and this is like sine, and this is cosine. So if I get this sine over here, this is simply going to be transformed to minus 1 over 9, 1 over x plus c. And so it's a very simple transformation. If I want to, I can come back and see it in terms of a different substitution, but overall this is going to work out very well for what we want to. Now to conclude this video, let's go over one antiderivative that we already know. So because we know that the derivative of arctangent of x is 1 over x squared plus 1, then it kind of makes sense that if I integrate, I'm just going to return to what I have, right? This is going to be part of something that we're going to check later that is called the fundamental calculus theorem. But it kind of makes sense, right? We're taking the derivative of a function, it gives me this, and now I'm taking the integral of that derivative and go back. It should give me the original function. Well, let's actually prove that this occurs. And so as before, we saw that this step of x squared plus a squared substitution, it gives me the x equals a tangent of theta substitution. And so of course in this case it's 1, a is 1, so it's just going to be x equals tangent of theta. And so if I plug that in here, this is just going to give me 1 over tangent square of theta plus 1 times secant square of theta the theta. And so this is again tangent square plus 1 is secant square as well. So this is going to give me secant square over secant square. Okay? And so that means that this integral is the integral of 1 d theta. And so pretty much this is just going to be theta plus c. Okay? So now what's going to happen with this is that we're going to use this and x equals tangent of theta, and so theta is going to become arctangent of x. And so that's why then this becomes here arctangent of x plus c. Okay, so this is just to verify the relationship between this particular function and their derivatives. Now, trigonometric substitution is something that, of course, can be done with definite integrals as well. And we can also do it with the weird trigonometric hyperbolic functions that we've seen before. So the next video is going to be on those particular examples.